Okay, so I forgot to mention this at the beginning of the course, but we will assume that every person that we talk about here, especially femboys, will follow the QFT. But not the QFT, sorry. The QTC, or the quantum trap configuration, or rather the standard. So it's an SQTC. So standard. You can spell standard. Standard quantum trap configuration, and this assumes that the mass is 1. What else? What else do we assume? If the mass is 1, if P is in it, or actually basically all quantities are labeled as 1. So I believe if spin is involved, I think it's just 1 as well. Of course, we assume also that H is Planck's constant. Assume H is Planck's constant, H bar remains the reduced Planck's constant, which is H over 2 pi. And yeah, I believe that's it. So mass 1, H is just Planck's constant, and H bar is the reduced Planck's constant. You know the usual stuff, except we just assume that mass is 1. And we assume that of course this is for a discrete object. If we're talking about a light quanta, I believe it's massless, because photons don't really have mass. So if we're talking about the person or femboy or a trap as a light quanta, then we assume that it's massless. Okay. The reason why we're doing this is because we don't really care about the mass of the object, right? We don't really care about the mass because that really has no effect on their behavior. So we want that mass to be unitarily. So that's the standard quantum trap configuration. And we will stick with that for this course, for the rest of this course. Okay, so here are some additional things that we want to say. So if I let P be the momentum, or as we call it, it's the change in the behavior of the system with respect to time, mostly the change in the maybe with respect to position, momentum is h over lambda. We're in h, of course, as I said a while ago, is the reduced Planck's constant, or no, it's just regular Planck's constant. Just regular Planck's constant. And another thing here. Now, how do we derive this? Now recall what Einstein said, which is E equals mc squared. The energy is equal to the mass times the constant of light squared. And then recall that the momentum in classical mechanics is the mass times the velocity. Okay, so now rearrange this equation, we get m equals E over c squared. And notice that I think according to the de Broglie relation, E is equal to Planck's constant times the frequency of the wave. So that's just the velocity of the wave, and h bar is practically its mass. Or rather, well, really it's just another way of restructuring E equals mc squared. Okay, and then Now, you notice that notice now that P, when you quantize it, is H times F over C. Okay, but we notice that lambda is equal to the frequency over constant of light, the speed of light. So now the momentum P is equal to h bar over lambda. We just replace lambda F over C, I believe, just F over C. So this over here, we just apply some stuff here and then we get this, and then we just replace lambda with FC, or equate lambda with FC, and then we get the final result, P equals h over lambda. So that means the momentum of a particle, or actually a wave, because we're talking in terms of wavelength. When we talk about lambda, here is a wavelength. So if I have a wave, the wavelength is the distance between two crests. Yeah. So, yep. And one other quantity that we want to talk about is the angular frequency, which we will call omega. Omega. So if you were to wind this wave around a point, around a circle, let's say we have a point, we have a circle, and then we wind this wave around it, so it looks like this. It looks like a bit of a flower. Of course, we make it more continuous. Continuous there. A tangent vector at any point is the angular frequency, and the distance between any two crests, not rows, is lambda. Remember from classical mechanics. Okay, so now given these quantities, the de Broglie relation yields the following. So the energy of the system our wave is describing is equal to h bar over omega, or h bar times omega. And equivalently, the momentum is equal to h bar times beta, which is the phase constant. Beta is the phase constant. So the momentum is proportional to h bar, which is the reduced Planck's constant. So I'll write it down here as h over 2 pi, beta h over 2 pi. So it's proportionally related to the phase constant. Energy is directly proportional to the angular frequency. So I'll call omega angular frequency. So when omega really only applies when we wind a wave around a circle. Now, there are many different ways of expressing the Schrodinger equation. Now, the Schrodinger equation I talked about in the past two lectures is really only the one-dimensional case. So recall that the Schrodinger equation is an equation that a quantum system satisfies. So if we have a wave function assigned to or probability density assigned to a quantum system, we want that probability density to satisfy this equation, or these equations. So one-dimensional, is just what I wrote out in the last few lectures and also tried solving. So this is just minus h bar squared times the reciprocal of twice the mass times the second partial derivative of the wave function with respect to x. That's equal to the energy operator times the wave function, which is I h bar times the wave function. Oh, I'm sorry, one more thing. The partial derivative with respect to t. The first partial derivative with respect to t of the wave function. Now, the second dimensional case is the same thing, but we have two dimensions this time. So I'll put this in a parentheses. Plus, so we have a second spatial derivative. Spatial derivative. And we're taking the sum, and we're applying that on our wave function. So now it's this, and then I h bar of the wave function. So primarily the wave function depends on two variables in the one-dimensional case. It depends on time, and it depends on the position with respect to the x-axis only. Now, we have a two-dimensional case. Just so you know, time here is not its own like line or its own interval wherein the wave function is going to span, but rather it's some temporal dimension that's abstract, and then it's some slider, abstract slider that's such that when we slide it, the system changes. Okay. Okay. So the three-dimensional case, it's actually a bit tedious to write out, so I'll use what's called a Laplacian operator, which is just the sum of the second derivatives of the sum of the second partial derivatives dot with this. So it's the dot product. So primarily, the Laplacian operator is a vector function or a vector operator, and is primarily like this. So partial xn, partial yn, and partial zn. Okay, and then when we take its dot product with something else, like say this, we just get the sum of the products, right? So Laplacian n dot a function f gives dn x plus dny plus dnz times f. And so, so the three-dimensional case is just first squared, so m to the minus 1 times the Laplacian squared of the wave function is equal to the energy operator, which is equal to I h bar times the spatial, the temporal derivative of the wave function. So this is the third-dimensional case. So as to two dimensions here, we have a wave function now that's three-dimensional, or the wave function must be three-dimensional, and it's giving us the probability densities, or rather, when we take the norm squared of this wave function, we get some probability density that gives us the likelihood of finding the function at certain points in time. So we have two-dimensional points here, so we have to consider two spatial directions, or 2 degrees of freedom, or 4 degrees of freedom. And then here in the three-dimensional case, we have to consider three-dimensional degrees of freedom, and then now the wave function of this entire system with respect to the position, the wave function with respect to the position of this entire system is now dependent on some abstract 4-dimensional space. So instead now, like time, we're now going to think of the wave function as some slider. So given 3 points, right, or 3 states of the system, we are now assigning a value, a real value, which is the wave function at that point, or rather the norm of the wave function at that point, which gives us the probability that the particle is at that point. So how does this apply to rigid dynamics, right? How does the formulae that I just described apply to rigid dynamics? Okay. So now, how do I describe this? Think of, so recall Reggie calculus. So velocity, we correspond velocity to a new quantity, which we call the change in affection, I believe, or change in, let's name it the change in affection. So our main quantity that we want to consider here is affection. So we're now thinking of affection as something that's akin to energy, that can neither be created nor destroyed, but rather transformed and stuff like that. So velocity is the change in affection with respect to time. So now we have some line which we call A, and then we're now considering the change of a point, or the derivative of a point, with respect to time. Okay? So let's say that the affection is here first. As time goes on, and suppose that the affection changes to something that's higher, so we get more and more, we are more and more in love with the person, right? Then it sort of increases, or the spatial derivative tells us the change in what happens, or the change in that with respect to some unit of time. Okay, so if we correspond velocity here with the change in affection, so an equivalence relation, so it's somewhat similar but not particularly exactly similar. Okay, so we assume now, remember that mass is equal to 1, well, according to, at least according to SQTC, according to SQTC, I'll rewrite that. 1 on SQTC. Mass is equal to 1. So the sort of momentum, as we call it, so the behavioral momentum is just equal to the change in A with respect to the change in T. Because we assume that our mass is 1, actually the mass can be arbitrary because it really doesn't depend on anything. You can say that, well, it's the change in the affection with respect to time, times the sort of mass, quote unquote. We really don't know these quantities. These quantities are very abstract, and that's another reason why you shouldn't apply this like other theories. You really shouldn't apply this kind of stuff. It's kind of if my cat is here, right? Because Schrodinger's cat. Okay. So if we let this be the change in affection and change of time, now m here is a proportionality constant, which we can actually think of. We can think of m as some how much affection is in a given, how much affection is in a person, say. Like how mass is how much atoms are inside an object. We think of mass this time as some quantity, or one measure of A, one of many measures for A. Or the affection. And it could be some weighted value, or it could be expressed in kilograms or whatever. But let's just say it is one of many measures for A. But it is not precisely A itself. It's just that A can be expressed in many different quantities, and M is just one of them. So the momentum is this. So, well, the momentum. So practically where the love is going, or where the affection is headed towards, right? So if we're thinking of it in the one-dimensional case, the vector of this of the vection here at this point, as I illustrated, is headed towards this way. So its momentum is headed towards that way. And FYI, momentum here is a vector quantity, not a scalar quantity. So that's the magnitude and the direction. Because it's composed of some vector scaled by a scalar. Okay. So how about the P equals h bar over lambda now? Okay. So suppose that a vection is modeled via a wave. Suppose. Or actually, instead of just thinking of a vection, let's think in more general terms. Let's say the change in the behavior of the person. So, when we say the behavior here, we're talking about what they identify as and things like that. So, different states of a person. So, let's say at some point, let's say the person's gender fluid, right? At some point, XY, right? If we recall our O cross P axis from Femboy theory, the appearance and the orientation here can be thought of as some quantities that are more general of A. So, okay, so instead of just thinking of A, let's think about two different quantities which can be states of a system. So a person here can be expressed as some vector, shall we call V, which is some linear combination of these two vectors, which I will call spin side and spin up. So now V, the vector V, or a person, I would just call it P because it's not really P, but let's call it Q, or yeah, Q is now it's expressed as a linear combination of Q times the spin up plus Q times the spin side configuration. Where spin up, it's just the vector 0, 1, and then spin side. This is just for compactness sake, okay, notation sake, is 1, 0. So the matrix associated with this system is a unit matrix, 1, 0, 0, 1, unchanged, and usual basis vectors. So okay, now suppose that this vector changes, right? Or suppose that these states change as time goes on. So as we move the abstract slider of P forward, this changes. So Q changes. There's a corresponding change in the spin side state and the spin up state. Okay, and that is measured by the partial derivative, by the derivative, because derivative measures infinitesimal rates of change. So okay. So now, instead of just thinking of A is a good intuition of thinking about these things. Change in affection. Instead, let's think about the change in the behavior or change in the attributes of a gender fluid person, or maybe a person who isn't quite so sure about their sexuality, right? So, the quantity dq corresponds, or well, it's at least equivalent to some change in the state. Okay, so if you think of it now as a change in behavior or change in the attributes of a person, so I'll call it Q this time. So Q is a state, or I'll call it ket U. Ket is just a notation. If you recall position theory, you'll understand this. Or it's really just this. So Q ket, or ket Q is that. Okay. No, I'll change markers. Oops. Okay. Let's change markers. Okay, it's the same way anyway. Okay. Okay, so with the corresponding change in Q, or Q is just the attributes here. But what we really want to do is quantize this and make this into some probability density that depends on it. So now what we want is associate Q with some wave function, which we will of course call psi now. Now Q is associated with some probability density function because we cannot be fully certain about the behavior of a person, right, with respect to some point in t or some instance in t. So we're supposed to associate this Q or this system with its own, with its own wave function. And of course, because this is a vector quantity that's expressed in this ket, the wave function would also be expressed in some ket here. And so this now would be corresponding to some alpha times the up state plus beta times the side state, where alpha and beta are complex valued functions. So functions that take C onto C. So take C and map it onto itself. So their image exists in some C2. Okay. Okay, now that we've kind of rephrased the theory in terms of a more general and more in a generally better way, now let's talk about, actually let's rephrase what we said about momentum. So now the momentum P is equal to, of course, Rm, which is a measure of some proportionality concept. Now, we don't think of this intrinsically as mass. Think of this as some abstract number, some number in R or Z maybe, that we multiply to make this proportional to the change in the behavior, or the state. So dTQ. That's now our new thing. Or if we quantize the system and think of it in terms of probabilities, it's now M, or rather, because it's a quantum object now, according to the de Broglie relation, it will be P H bar B. Or it's really it's really M times the derivative with respect to the psi, with respect to Q, of course, or the variables of Q, which is O or P, O, P. So that's our new reformed momentum. Now, if we think of it as a light particle now, remember from a while ago that P equals h bar over lambda. Now, think of this as some distance between a wave. So if we express the behavior in terms of some wave, if we express the behavior as some wave, think of lambda as some distance between two peaks. So just recall your femboyology. Suppose this is M, suppose this is F. Lambda now is the distance between a point in time wherein the person is M, and then, and another point in time wherein the person's M. Or it could be F if you just switch the positions of the two. The position doesn't really matter, it's arbitrary, but let's just say, for example, this is M and this is F, okay? Yeah, so that's just the distance between these two. So the time between one instance where it identifies as male and another instance where it identifies as a male. So it's a peak, the maximal value of the maximum maleness, you'd say, of the person, of the system. So that's it expressed in terms of that. So this can be expressed as h bar times, well, now there's a difference really. So t, or q to the minus 1 of some m, maximal m, maximum of the image of Q minus some other times max 2 of some second image of Q. Close it, close, and then close. So this is just the t value of this image of Q, which tells us the maximum image of Q. So that means it's the highest point of Q. And then this is just the t value of another maximal value, or local maximum of Q. Or if we think if we quantize it like we said a while ago, h now is equal to psi the minus 1 of the maximal value of the image, or max 1 of psi minus another psi to the minus 1. So now we're talking about probabilities. Max 2, or so because we're talking about maximal values, it's O now and P. Let's move this a bit. O, P. O, P, max 2, image, O. Now this may look a bit complicated, but it's really just telling us the probability here. So, or actually the non-square or the inverse square of the probability density. And not the inverse square, but rather the square root of the probability density. Is equal to just the square root of its probability density. Because every wave function has a probability density associated with it. And we'll just define this wave function, at least this one, as that. So as to shorten the notation. Now you're thinking, how is it not expressed in terms of states? I mean, this is it's supposed to be expressed as some as a function, a vector function, a vector function. But let's just assume that it is a vector function. For now, it's just this. However, we can express it. Yeah, you can express it as a vector function, but it would it's a bit tedious. So, but I'll say it here anyway. So it's really an operator. That's the thing. So okay. OP close, then max 1. So the maximum vector the image of this gives OP. Oops. Okay, I'm not gonna write the parentheses here anymore because this is already thing, and you can think of it as some image already. Minus some, of course, vector function. Now, instead of it just being a vector function, we can now think of this in terms of some matrix, some Hermitian matrix that acts on the system. And then next we can think of these now as some eigenvector of the system. Or some vector such that when we apply this, this vector here would satisfy some p over here, some constant. So now this is actually a matrix now. Instead of just some vector. Max 2, image, psi, OP. There. So that's the wavelength, at least for in the sense of when we think of it. So this is the original one. This is the one wherein we think of it as an operator, and this is where we think of it as a matrix now. Okay. So that's splendid. This is hard to erase these things. I always have to spray. Okay. Leave some mark here. I don't spray. So now let's talk about energy. So energy now, energy, in the at least the quantum sense, is equal to h times the frequency. Now the frequency is basically, if we let time elapse, the frequency is how fast the wave moves if we let t slide on. Because primarily, what we see is just the wave itself expressed in terms of t and some other quantity, mainly O or P. There's no really telling if it's moving or not unless we let t slide. And when we let t slide some amount, like some small infinitesimal amount, there should be a corresponding movement in the entire wave. And the movement of that is precisely the frequency. Now, compared to wavelength, which is a distance, right? It's really a scalar value. This here is a vector quantity. I mean, the other one's scalar quantity. This is a vector quantity. So now, if we express in terms of wave, so this time we think of a person as a photon that's acting as a wave, not as a particle, equals hf. That becomes h times the switch derivative with respect to t of our, not really the wave function, but our system. So Q. Now you notice this is painfully close to the energy operator in the Schrodinger equation. And in fact, yes, to quantize this or make this fully the actual energy operator, so actually primarily Q is not part here because we assume the Q is already dictated by this entire thing. You notice that we just quantize this by reducing it. So now E is mapped to E hat via the assumption that we make H equal to H bar, or we turn H, or under some, okay, I need more space. E becomes E hat through where we map H onto H over 2 pi. And so when we put things together, E hat is now, or actually I, and then it's I. We add an I to that also. So now it becomes I H bar, that's the time derivative of the system. Or if we want the system to be dictated by probabilistic stuff, just say I H bar dt times the wave function. And now that is precisely the right-hand side of the Schrodinger equation. That's pretty neat that from this classical looking thing, we can derive something that's quantum mechanical. That's truly quantum mechanical. I think that's pretty neat. And of course, as we dictated in the last videos, this wave function must collapse to 1 or vanish to 1 when we take its integral from minus infinity to positive infinity. Yeah. Okay. More. Okay. Okay, one more, let me see. Yeah, let's take a small break, I believe. I'll let you absorb this information. Okay, so the next concept that we want to talk about is really the collapse, the real collapse of the wave function. I've been alluding to this a lot. So this is where we actually talk. This is where we talk in depth about Schrodinger's Femboy. Oh yes, you guys wanted to talk about this a lot. So I got a lot of views in that video. So let's talk about it again here. So suppose we have a femboy, a bisexual femboy, or an androgynous femboy that would look great in a maid and a tuxedo or a suit. And we put the femboy in a room, no windows, and a door, which we can't peek through, okay? And it's also soundproof, okay? So, yeah, we put the femboy in a room, we put them in a room, put the femboy in a room. There's a door, but we can't peek through it. The walls are soundproof, so we don't hear him conspiring with himself or thinking, oh, maybe I should do this, maybe we should. You don't hear him at all. You can't see him, no windows, and you put a maid outfit or a skirt. Put a skirt in there. A skirt or a tuxedo. Forgot to draw these things. So the point is, you get a maid and you put them in a room with a tuxedo and a suit, I mean, and a skirt. Okay. So there are two possible states that the femboy can take on. So the femboy can either wear the suit wherein he's masculine, wear the suit wherein he's feminine. So there are two possible states that the guy can take on this time. And these can be thought as waves now, as waves of probabilities. Okay? Waves of probabilities. So maybe a Gaussian distribution. Or maybe a sinusoidal one, where it's a bunch of probabilities. Maybe at this point in time, we let time move forward, by the way, okay? Maybe at this time here, or maybe it's likely that he's, there's a likelihood, or if we superimpose the two probabilities, right, or their own wave functions. So there's a wave function for M, and there's a wave function for F, or at least the norm of those wave functions, which would give us probability amplitudes. And then suppose, alright, let's, and then what we want is that this over here, of course, we want this to satisfy the property, so, and, I don't know if you guys can see that. Yeah. Satisfy, so this integral, let's write that properly. Integral minus infinity to positive infinity with respect to x, or the position, right, or whatever they're identifying as. So actually it's O. This is actually I actually talked about this back in femboy theory as a footnote of the square of this wave function is equal to 1. So both of these satisfy this condition, okay? So as O goes to infinity, or off to minus infinity, and we take the sum of the areas, they all correspond to 1. And so let's say that this is over here. The opposite. Sorry, it's the opposite. This time it has a low probability density here, and then a high probability density. So this extreme here is the feminine part. This extreme here is the masculine part. As we said in femboy theory, right? We restricted some values and we assumed that we're following femboy theory. Let's make that more cleaner. Okay. And then this is of course, wave function squared. And then this is O. Okay, so we don't know yet whether this is exactly the femboy's wave function, and neither do we know that this is the wave function of the femboy, because for all we know, he could actually have a 50-50 chance of wearing one of them, both of them, or none of them. So really, when we don't know, or we're not certain about what exactly is going to come out of that room, what we do is assume a superposition of both of these probabilities. So we'll notice now that according to our quantum objects and quantum mechanics in general, the norm of the wave function of our femboy, actual ECT squared, is just a superposition of these two. So add up those probabilities, those probability densities. All right. M plus F. And then this is so O component. So I just add each function. So it will become slightly bigger than you expect, or than what we used to think. So sorry, it's not precisely that narrow. And then assume this is not the scale, okay? So yeah. So this is our superposition of both of them. And until the femboy comes out of the room, this is the actual wave function of him, right? Until we open actually this is the most important concept of quantum mechanics. Until we open the door to the room the femboy is in, this is his wave function. This is the wave function of the femboy in there. Okay? And of course, we're assuming that this wave function satisfies Schrodinger's equation and satisfies this condition here as well. All right? Well, of course, I didn't write it there. Right here. Integral from infinity to positive infinity of this with respect to O, the wave function. So just so you know, the wave function here is just dependent on O, just the appearance, not really the orientation or the preference. Okay. So it's equal to 1. That's equal to 1. Okay? And everyone cool with that? Okay, so yep. So okay, let's open the door. So the psi actual, or the actual wave function, can collapse onto one of two states, right? And actually, because we have a 50-50 chance of doing it. Wait. Oh, I'm kind of wrong, because this would give us very narrow graphs. So actually, this isn't the square rather, but just the regular wave function of them. Yeah, and then what I said a while ago was not the square, but rather just just that. Okay, so I'll just rewrite it here. V actual, or psi actual, is this. Yeah. So this is the actual thing. Okay, this is the. Frick, I screwed up. Okay, yeah, this is the actual thing. This is actually what I'm saying. Okay. Yeah, this is the actual thing. When we take the norm, of course, this is a complex value, and then this is a complex plane. Okay, so this is not in R2, but rather R cross C. R cross C Z, or R also. Okay. So okay, once we do open the door, the wave function collapses into something else. So it either collapses. The wave function is either psi f or psi m. And in fact, because we actually started making an observation, that's when we take when we take, that's when we actually take the norm and then the square of the wave function. No observation. And then there exists an observation. So we made an observation, and then here is no observation. So now we actually made an observation now, and then let's say that the femboy comes out as wearing the tuxedo. So now our actual wave function squared is precisely this. Oh, sorry. 4. Oh, this is 4. Collapses to F. So this is F. And then that's for when he comes out in the maid costume. And then now this one is 4. Wave function actual collapsing into psi F. Excuse me. So there you have it. So actual. So there it is. So we collapse into one of these. Of course, this is when we made our preliminary observation. So we are fully certain that they are male because we have seen them wear the tuxedo. And then we are fully certain they are female because we have seen them wear the costume. Just like when we make an observation that a photon is somewhere, right? We see the photon at some position. Our wave function or the probability density of us finding it is 100% there and 0 elsewhere. Likewise here, our certainty or the probability of them being a male is now 100% this one and 0% anywhere else because we've seen them with absolute certainty that they are wearing the tuxedo or the maid outfit, whichever. So the collapse of the wave function is a very important concept because without making an observation, we are just left with a complex value thing. We are just left with probabilities as we know them. Or where we think the system is at or what the system is, right? But when we make an observation, our probabilities start to become 1 at one certain state because we've seen it being that state. And when we see that state or when we see that femboy or that system being that state, that is exactly what the probability gives us or what the probability should give us. That it should precisely be 1 or 100% that system state or when we make the observation and the system does enact that state. Now, if for some reason that the femboy doesn't wear neither of them, just comes out naked like he came in there and he said, I can't decide which, then surprisingly, our wave function is just 0 everywhere. So this is not 1, okay? This is just 0 everywhere. So I'll just write here 0. Is equal to 0 for when it collapses, psi actual collapses onto, I'll negate it, neither psi m or psi f. So when the femboy, so there are 3 possible states here. Of course, the femboy knows that if he tries to wear both the suit and the maid outfit, he'll look silly, so he won't do that. So there's 0 probability he'll actually do that, no matter what we say here. Let's just assume, okay? There's plenty of assumptions to be made here. This is physics after all. We do make assumptions to make things easier for you to understand. So if you do want to factor in the fact that he might wear the maid outfit and the suit at the same time, you know, real girl boss energy, then I suppose you can say that it collapses onto a sum of these 2. So there's the 4th case, unlikely case, is that psi actual collapses onto a sum of psi f plus psi m. Yeah, but we're going to disregard that case for now. What we want to consider is 0. So the wave function now, is 0 everywhere if the femboy comes out of the room and says, nope, I just can't decide. It's too hard to decide. Okay. So if we include the fourth case here, we really have a 2.5 or 2.5 chance of one of these happening, right? Assuming uniform probabilities. And this is a uniform probability. So, but a while ago, I showed you guys that there is some likelihood that if they primarily start at us thinking, oh, maybe I might want to dress up as the tuxedo. Oh, there's some, when he's strongly thinking about wearing the tuxedo, right? Maybe there's some thoughts where he wants to maybe wear the maid outfit, and that's what we were showing a while ago with the two crests, you know, the two probability amplitudes are actually a square root of the probability amplitudes. So yeah, and that's another reason. It's very neat because the reason why this here is squared, right? You notice that these wave functions or these probability amplitudes are very narrow and tall, right? But when we take their square root, when we actually obtain the wave function itself and not just the norm, then we get something that's more narrower. In fact, that's the square root. So that's pretty neat. That's pretty neat mathematical observation of all of this. So yeah, that's it about this lecture. And yeah, sorry this took a little bit a while. Sorry for this noise. And sorry for the little break in the middle. I just had to gather my thoughts and stuff like that. I know I should have done this before the video, but it was better to do it spontaneously. So yeah, this is Schrodinger's Femboy, revisited, of course, and then we also revisited momentum and then rephrased it in terms of our language here and application in rigid dynamics. So I guess this is a good place to stop.